Come on, my dears, let us proceed further in chapter number 6. Kindly read this statement of illustration number 3. Read it? Look. Let us recall the formula for number of moles. That was mu. You have studied in second semester. There were two formula for finding number of moles of atoms. Those two formula were mu equals to n upon Na and mu equals to m upon m0. Please remember this, both the formula. Mu equals to n upon Na, mu equals to m upon m0. Fine. Just give me identification of each symbol. This is number of moles of atoms. This is total number of atoms. This is Avogadro number. This is given mass, and this m0 is atomic weight. Simple. Find out capital N from here. It will be m into Na upon m0. M into Na upon m0, give it equation number 1. Fine. Now, come on, capital U, that is uranium, you are given with atomic mass number 235. Which element is given to you? Uranium 235. Fine. Now, whenever atomic mass number is given to you and atomic weight is not given to you, then you may take atomic weight just equal to atomic mass number, but that many gram per mole. That many gram per mole. Okay. So right now they have not given atomic weight, and we are supposed to use that value. So what you should do? Atomic weight should be taken same as atomic mass number, but that many gram per mole. So atomic weight is 235 gram per mole. Fine. Tell me, what was the formula of activity or rate of disintegration? We had studied last time. dN upon dt equals to minus lambda n. dN upon dt equals to minus lambda n. Correct? This dN upon dt as it is, minus as it is, lambda formula everybody knows, 0.693 upon tau half into capital N, and we know capital N from here, m into Na upon m0, m into Na upon m0. Now this rate of disintegration, you should always take negative. Rate of disintegration is always negative. What is given to 9.3 into 10 raised to 5 disintegration per second. So this time you must take in second. Okay. 0.693 as it is, capital M as it is. What is Na? Avogadro number, everybody knows, 6.02 into 10 raised to 23 divided by tau half. As I told you, this time you must take in second. What is half-life given to you in the statement? 7.04 into 10 raised to 8, that many year. But at the same time in the statement they have given 1 year is how many second that they have given? 1 year is 3.16 into 10 raised to 7 second. So while converting time from year to second, you must multiply by this factor 3.16 into 10 raised to 7. And now it is m0, which is atomic weight. Just now I told you it should be taken 235 gram per mole. Come on, m0 is 235 gram per mole. Got it? When you are taking this in gram per mole, naturally this mass will be obtained in gram. And that mass of uranium, you will get nearly 12 gram. 12 gram. Okay, fine. Now mass of the specimen in the ore of uranium, we have taken some sample, some specimen, and mass of that specimen I am taking m dash. In that, how much is the mass of uranium? That mass we have found out, it is 12 gram. Okay, fine. Mass of uranium, they have given in the statement, it is just 0.72% of mass of specimen of ore of uranium. Mass of specimen of ore of uranium we have taken M dash, and it's a 0.72 percentage. It's a 0.72 percentage means multiply by 0.72 divide by 100. Okay, it is not 72 percentage, it is 0.72 percentage. So multiply by 0.72 divided by 100. Got it? Fine. Mass of uranium is 0.72% of mass of specimen of ore of uranium. Got it? Fine. Now this mass of uranium we have found out. Mass of uranium, capital M, we have found out. It is how much? 12 gram. So this mass of uranium we know it is 12 gram. This M dash as it is into 0.72 upon 100 as it is. Now find out M dash. It will be 1666 that many gram. So this is mass of specimen of ore of uranium. Got it? And this is the mass of uranium in that specimen. Okay? This value is 0.72 percentage of this value. Okay? Fine. Now kindly read the statement of number 4. Read it? Now tell me, what was the exponential law for mass? It was m equals to m0 into e raised to minus lambda t. Same formula written here. M equals to m0 into e raised to minus lambda t. What is this time given to you? As 1 upon lambda. Time is given to you in the statement equal to 1 upon lambda. 1 upon lambda means reciprocal of radioactive constant. It is nothing but average life or mean life, tau. Tau equals to 1 upon lambda. Simple? Fine. So this given time is 1 upon lambda. Now lambda will cancel. E raised to minus 1. Just transfer in the denominator. It will become e raised to plus 1. So 1 upon e into m0. What is value of small e? Base of natural logarithm. Its value is 2.718 into m0. 1 upon this, it comes out to be 0.3679 into m0. But if you want this value in percentage, then you should multiply by 100%. And when you multiply by 100%, it is 36.79 percentage of m0. So at the end of this much time, the undisintegrated mass is 36.79 percentage of initial undisintegrated mass. Correct? And now they have also asked disintegrated mass. Remember, disintegrated mass is always m0 minus m. That is initial undisintegrated mass minus final undisintegrated mass. Initial undisintegrated mass was m0. Final undisintegrated mass is m. m0 minus m will give you disintegrated mass. Okay. m0 as it is minus as it is. What is value of m? Without percentage. Because this value is without percentage, this value also should be written without percentage. It is 0.3679 m0. 0.3679 m0. m0 if you take common, inside the bracket 1 minus 0.3679. 1 minus 0.3679, it is 0.6321. That many m0. And now if you want this value in percentage, you may multiply by 100%. Then it is 63.21 percentage of m0. So what we have proved, for every radioactive element at the end of time equal to its average life or mean life, it so happens that undisintegrated mass is 36.79 percentage of initial undisintegrated mass, and disintegrated mass is 63.21 percentage of initial undisintegrated mass. Got it? Fine. Now kindly read the statement of number 5. Read it? Come on. N equals to N0 e raised to minus lambda t. Exponential law. Simple. Now what is this N0? Initial undisintegrated number of atoms. Correct? Number of undisintegrated atoms at time t equal to 0. Let it be 100. Correct? Now what have they given in the statement? That 80% number is getting disintegrated. No problem. Out of 100, 80% is getting disintegrated. No problem. What is left? 20%. What is left? 20%. And what is 20% of 100? It is 20. So this number of undisintegrated atoms is only 20. Is only 20. So when N0 is 100, N is 20. N0 is 100, then N is 20. So N is 20. N0 is 100. N into e raised to minus lambda t as it is. Fine. Now take this 100 down. So 20 upon 100, that is 1 upon 5. Take this part down in the denominator on the same side. So 1 upon e raised to plus lambda into t. Power will become from minus to plus. And now take cross multiplication. So e raised to lambda t will be equal to 5. And now take logarithm to the base e on both the sides, that is natural log. Come on, lambda t. Power will become multiplier, lambda t into natural log of e. Here natural log of 5. What is lambda? By formula 0.693 upon tau half into t. Natural log of e means log e base e, which is 1. This is natural log of 5 means what? Log 5 to the base 10. And from your log table you will get it. Wait. First of all, natural log of 5, that is log of 5 to the base e. Now base e to base 10. Base e to base 10 you must multiply by 2.303 log 5. Here ln means natural log means having base e. Here log means having base 10. Base e to base 10 you must multiply by 2.303. Now place the values. 0.693 as it is. What is this tau half? Half life. You are given in the statement 0.693, that many hour. If you are taking this time in hour, this also will be obtained in hour. So let it be t as it is. And natural log of e means log e to the base e, which is 1. 2.303 as it is. Log 5 to the base 10. In your log table it comes out to be 0.6990. 0.6990. And now this 0.693 will get cancelled. Left is only t. And 2.303 into this, that multiplication comes out to be 1.609797, that many hour. Okay. Because you have taken this time in hour, naturally this also will be obtained in hour. Symbol of hour is not HR. No, no, no. Only small h. And no full stop. Okay. Can you read the statement of number 6 now? Illustration number 6. Come on, read it. Tell me. What have they given? They have given two radioactive elements, A and B. A is parent element, B is daughter element, because A gets converted into B. Correct? Fine. For element B at time t, for element B at time t, see some of the symbols, try to understand. Time rate of change of number of atoms in element B at time t, time rate of change of number of atoms I am taking, come on, dN by dt. Fine. Now at the same time in element B only, time rate of increase of number of atoms. Time rate of increase of number of atoms, let it be alpha, because they are given in the statement the symbol alpha. And why I am writing time rate of increase of number of atoms? Because as parent element decays, it gets transformed into daughter element. So as time passes on, the number of atoms in daughter element will go on increasing. That's why I am writing time rate of increase of number of atoms, and which they are given as alpha. And not only that, they are given that alpha remains constant with time. Fine. Then the time rate of decrease of number of atoms. Time rate of decrease of number of atoms, I am taking minus lambda n. Why? Time rate of decrease of number of atoms, because the element B is also radioactive, so it will further decay. So number of undisintegrated atoms in element B will start decreasing. That's why I am writing here time rate of decrease of number of atoms in element B, and that is nothing but rate of disintegration. Its formula is minus lambda n. Minus lambda n. Fine. Now this is net rate of number of net rate of change of number of atoms. Net time rate of change of number of atoms in element B. It should be equal to time rate of change of increase of number of atoms plus time rate of change of decrease of number of atoms. Time rate of increase of number of atoms, it is alpha, and time rate of decrease of number of atoms, it is minus lambda n. So I am writing minus lambda n. This is rate of increase, this is rate of decrease, and this is net time rate of change of number of atoms in element B at time t. Fine. Now this whole part, just put it in a bracket, and that whole bracket you may bring down in the denominator on left side, dt you may take up. Okay, fine. Now tell me, take integration on both the sides. Integration 1 upon alpha minus lambda n. Integration 1 upon alpha minus lambda n dn, and that equals integration 1 dt. Integration 1 dt. See, here variable is in terms of time, so limits also must be specified in terms of time. Initial moment we take t equal to 0, final moment we take t equal to t. At initial moment, the number of undisintegrated atoms in element B, they have given as n0. At the end of t time, number of undisintegrated atoms in element B, they have given as capital N. Fine. Now integration of this function comes out to be this much: natural log of alpha minus lambda into n divided by derivative of this part with respect to n. When you take derivative of this part with respect to n, derivative of alpha is 0 because alpha is constant, minus lambda is constant, and d by dn of n is 1. So it is 0 minus lambda into 1. 0 minus lambda into 1 means what? Minus lambda. Correct? I repeat. Integration of 1 upon fx. It is natural log of fx. Natural log of fx. So natural log of this same function I am writing, and divided by derivative of this with respect to n. Derivative of this part with respect to n, it comes out to be minus lambda. And from where to where? From n0 to n. From n0 to n. Integration 1 dt is t. It is from 0 to t. 0 to t. Correct? Now minus 1 upon lambda I just take separately in multiplication. Minus 1 upon lambda. And natural log of alpha minus lambda n. In place of n, I should write upper limit, that is n. After putting minus sign, instead of n, I am supposed to write n0 here. So natural log of alpha minus lambda into n0. And here instead of t, I should write t upper limit. After putting minus sign, instead of t, I should write 0. Now minus you may transfer here, and lambda you may transfer in the numerator. So right hand side will appear now minus lambda into t. Minus lambda into t. And if it is log a minus log b, then it is log of a upon b. Similarly, natural log of this minus natural log of this means natural log of this upon this. Natural log of this upon this. Alpha minus lambda n upon alpha minus lambda n 0. And now take anti-log on both the sides. Anti-log and log will cancel, giving you alpha minus lambda n upon alpha minus lambda n 0. And when you take anti-log here, if it is anti-log of x, it is e raised to x. Anti-log of y, e raised to y. Similarly, anti-log of this means e raised to this. So e raised to minus lambda t. Correct? And now take this here. Come on. Alpha minus lambda n equals to e raised to minus lambda t into alpha minus lambda n 0. And now what I am doing, this minus lambda n I just transfer on right hand side will become plus, and this whole term I just transfer from right to left side will become minus. Correct? And now tell me, I want only n, so I should transfer this lambda in the denominator on left side. Come on, n equals to 1 upon lambda, 1 upon lambda, into big bracket you may put this whole term alpha minus lambda n0 into e raised to minus lambda t, correct? I repeat, what will be n? Transfer this lambda in the denominator 1 upon lambda, and into big bracket you just put this whole term alpha I have written, then minus e raised to minus lambda t into alpha minus lambda n0, correct? Tell me what we have found out. Number of undisintegrated atoms in element B at time t. Got it? Now kindly read the statement of illustration number 7. Read it. Tell me. They have talked about two radioactive elements A and B, and the initial activity of their mixture they have given as 2 millicurie, correct? Come on. For element A, initial activity I just show by symbol I0 of A. For element B, initial activity I just show by symbol I0 of B. And because you are talking about mixture, you must add both the initial activities. That's why I am putting plus sign here, and that total initial activity for the entire mixture they have given 2 millicurie. Now initial activity of element A, they have given 3 times initial activity of element B. They have given so in the statement. This part as it is, and that equals to 2 millicurie. Now I0 of B plus 3 times I0 of B, totally 4 times. So 4 I0B equals to 2. Then find out I0B, it will be 2 upon 4. 2 upon 4 means 0.5 millicurie, correct? But what about I0 of A? It is 3 times I0 of B. If I0A is 3 times I0B, then just multiply this by 3. When you multiply 0.5 by 3, answer is 1.5 millicurie. So this is the initial activity of element B, and this much is initial activity of element A. Now after 10 days, what will happen? You will have final activity. What is the activity formula? Exponential law is I equals to I0 e raised to minus lambda t. Fine. For element A, I of A equals to I0 of A into e raised to minus lambda A into t, correct? Lambda A means what? Radioactive constant for element A. Come on, initial activity of element A, we have found out 1.5 millicurie. Multiply by small e. What is small e? Base of natural logarithm. By value, it is 2.718. Raised to minus lambda A means radioactive constant for element A, which they have given in the statement 0.1 day inverse. But remember, if you take this in day inverse, then this time must be taken in days, because the power of E should be unitless. If by chance you are taking this lambda in hour inverse, this time must be taken in hour. Lambda you are taking in minute inverse, T should be taken in minute. Lambda you are taking in second inverse, T should be taken in second. Right now lambda is given to you 0.1 day inverse, then this time must be taken in day, and that is why they have given 10 days. How many days? 10 days. Come on, what value may be any value, but the unit here you should retain day only, because this you are taking in day inverse. This T is given to 10 days. Now this multiplication comes out to be minus 1. So 2.718 whole raised to minus 1, you may transfer in the denominator. So 1.5 upon 2.718 whole raised to 1. And now tell me, this upon this, answer is 0.552, that many millicurie. This is final activity of element A after 10 days. What about final activity of element B? Similarly, we can find out I of B equals to I0 of B into e raised to minus lambda B into t according to exponential law. Come on, initial activity of element B. Initial activity of element B is 0.5 millicurie, and into E. What is E? Base of natural logarithm 2.718 whole raised to minus lambda B means radioactive constant for element B, which they are given 0.2 day inverse, and this time is given to you 10 day. Come on, this into this comes out to be minus 2. So this raised to minus 2, if you transfer in the denominator, will become this raised to plus 2. And now this upon this you can find out, answer is 0.067, that many millicurie. Wait, now our final answer is the final activity of whole mixture. When you want to find out final activity of whole mixture, you should add final activities of both the given radioactive elements. That is I of A plus I of B. What is I of A? It is 0.552. And what is I of B? 0.067 millicurie. Both the values are in millicurie, so you can definitely add them. And answer is 0.619 millicurie. Correct? Suppose they ask the same value in becquerel, suppose. Then first of all, millicurie you must convert into curie, multiply by 10 raised to minus 3, and then after 1 curie is how many becquerel? 3.7 into 10 raised to 10 becquerel. Got it? That way you can find out final answer in becquerel also if they ask. Okay. Now kindly read the statement of number 8. It's a very good example. Just read the statement 2 to 3 times, please. I am taking N0 as, just try to understand the interpretation. What does N0 indicate? Look here, number of radioactive nuclei, either you say nucleus or you say nuclide, one and same thing, nucleus or nuclide, you can take any word, okay, no problem. Number of radioactive nuclides or radioactive nuclei in this solution injected in the blood at initial moment. Number of radioactive nuclei in the solution which is injected in the blood at the initial moment. Got it? Fine. That is N0. And let us find out that value. Don't you know activity formula? I equals to dN by dt, and both of them are equal to minus lambda n. So I equals to minus lambda n. I equals to minus lambda n, but because I am placing here I0, here I am writing N0, correct? Fine. This is initial activity, this is initial undisintegrated number of atoms, got it? Now tell me, I0 as it is, minus as it is, what about lambda formula? 0.693 upon tau half into N0. Activity I told you, you must take always negative. So start with a minus sign. Initial activity, they have given 1 microcurie, converted into curie, multiplied by 10 raised to minus 6. But 1 curie is how many disintegration per second? 3.7 into 10 raised to 10 disintegration per second. Because you are converting this activity in second, this half-life you must take in second. Wait. Minus as it is, 0.693 as it is. Come on, tau half, that is half-life, they have given 15 hour, but hour will not do. Hour should be converted into second, multiplied by 3600 into N0. Minus will become plus. In textbook, you know what have they done? They have neglected this negative sign. Say except you should not neglect, because activity is always negative. So when you write here negative sign, minus will become automatically plus. Okay, so don't neglect that way. Come on, find out N0. Find out N0. It comes out to be 2.883 into 10 raised to 9. That many number of undisintegrated atoms, but where? In the solution. In the solution which is injected in the blood. Okay, fine. Now we take sample. We take blood sample of volume 1 centimeter cube. See, as soon as you inject that solution in the blood, in the entire volume of the blood, that solution will be getting mixed up, will be getting spread all over, correct? And from that blood in which that solution has been mixed up, from that blood we just take a sample of only 1 centimeter cube volume. Now I am talking about that sample now. For that sample, for blood sample of 1 centimeter cube, at time t equal to 0, number of undisintegrated atoms is suppose n0 dash. This initial number and this initial number, both of them are different. So I am giving different symbol here, n0 dash. Fine. At the end of 5 hours, that number is smaller than this, let it be capital N. Now one result we had proved last time, at the end of time equal to n times half-life for every radioactive element, it so happens that number of undisintegrated atoms becomes 2 raised to nth part of number before that time interval. Okay, so we know this result, why not to use it? Now here instead of n0 I must write n0 dash, because I am starting with this number. From this number that number reduces to this number, correct? N equals to n0 dash upon 2 raised to n. At the end of how much time? Equal to n times half-life, equal to n times half-life. Now if both the times you are taking together, you must be taking in the same unit. This is given time which you are given 5 hours. Because this you are taking 5 hours, this half-life should be taken in hour. Both these times must have same unit. And as it is, half-life is 15 hours given to you. Find out n. It is 5 upon 15. 5 upon 15 means 1 upon 3. 1 upon 3 means 0.3333. Correct? N equals to n0 dash upon 2 raised to n. What is n? Let us find out. Come on. This is the formula for this. You know I equals to minus lambda n. As such, I equals to dn upon dt. I equals to dn upon dt, which is minus lambda n. Correct? Now, I as it is minus as it is lambda. What is lambda formula? 0.693 upon tau half into n. Just find out n from here. So it is minus I into tau half upon 0.693. Minus I into tau half upon 0.693. And that equals to n0 dash upon 2 raised to n. Got it? Fine. Now tell me, this minus as it is. I told you activity should be taken always negative. What have they given now? For this sample of blood, that is 1 centimeter cube, for that much sample, what have they given in the statement? That this activity is 296 disintegration per minute at the end of 5 hours. Correct? Now disintegration per minute, then this time should be taken in minute. This minus as it is, and this activity I told you, you must take negative, so you must start with negative sign. What is the value? 296 disintegration per minute, then this time should be taken in minute. This half-life they have given 15 hour to minute multiplied by 60 divided by 0.693 as it is. Now this is n0 dash as it is, 2 raised to n. What is value of n? 0.3333. Come on, 2 raised to n. N value is 0.3333. Now from this, minus will become plus, and find out n0 dash. Okay, it comes out to be 4.878 into 10 raised to 5. Correct? These many number of undisintegrated atoms were there initially in how much volume of blood? 1 centimeter cube. So for this much number, the corresponding volume of blood is how many centimeter cube? Just 1 centimeter cube. Correct? But then tell me, the solution you had injected in the blood, in that solution, what was the number of undisintegrated atoms at time t equal to 0? That number was this much. And actually that number was in the solution. But because that solution is completely inserted in the blood, the total volume of that blood will have this many number of undisintegrated atoms. Correct? So for this many number of undisintegrated atoms, for this many number, if the corresponding volume of blood is 1 centimeter cube, then for this many number of undisintegrated atoms, either you may say in the solution or you may say in the entire blood, because solution is mixed up in the complete blood. So for this much number, what is the corresponding volume of blood? It is this into this upon this. So this into this upon this, if you find out that volume V comes out to be 5910 centimeter cube. At the same value you can rewrite 5.910 into 1000 centimeter cube. But 1000 centimeter cube is nothing but 1 liter. So 5.91 that many liter. So this must be the volume of entire blood in a given body. Once again, actually we had taken 1 centimeter cube, correct, volume of blood sample. How much volume? 1 centimeter cube. And in that, this was the initial number of undisintegrated atoms. At time t equal to 0, initial number was this much, correct? So this much number is there, meaning thereby the volume of blood is how much? 1 centimeter cube. So for the same number I am writing corresponding volume, how many centimeter cube? 1, correct? But tell me, this many number of undisintegrated atom you had in the solution, but the solution is injected in the blood. So that solution is getting spread in the entire blood. So entire blood will have this many number of undisintegrated atoms at time t equal to 0, correct? Fine. So for this one number of undisintegrated atoms, if volume of blood is 1 centimeter cube, then for this many number of undisintegrated atoms, this many 2.883 into 10 to 9, correct? For that many number of undisintegrated atoms, what is the volume of blood? This into this upon this. That comes out to be this many centimeter cube. That is this into 1000 centimeter cube. 1000 centimeter cube is 1 liter. So it is 5.91 liter. Correct? That will give you total volume of blood in a given body. Correct? Fine. Now kindly read this statement of number 9. Read it? Fine. See, this small n I am taking as number of beta particles or electrons which is emitted from the surface of a sphere. But how many electrons are emitted from the surface in 1 second? It is just 40% of number of beta particles emitted from the atoms in the radioactive material in that sphere. The number of beta particles emitted from the atoms of radioactive material inside the sphere per second I am taking capital N, and whatever is that number, it's a 40% number is getting emitted out of the surface of that sphere. So this emitted number is number of electrons emitted from the surface of the sphere is just 40% of this number. Okay, 40% of this number means what? Multiply by 40 divided by 100. Okay, I repeat, what is small n? Number of beta particles or electrons emitted from surface of the sphere. Okay, and what is that capital N? Capital N is number of beta particles emitted in 1 second from the atoms of radioactive material inside that sphere. Correct? Fine. This number is 40% of this number, and we are talking about right now in 1 second. Okay. Now this number is given to you, 5 into 10 raised to 7 beta particles are emitted per second, and it's a 40% means multiply by 40 divided by 100. Now this answer is 2 into 10 raised to 7, that many electron per second. Now tell me, as the sphere surface of sphere loses electrons, correct? Naturally the surface would get positive charge. So as more and more electrons are removed from the surface, you will have deposition of more and more positive charge on the surface of the sphere. Then don't you know, potential on the surface of sphere is just equal to kq upon r, k into charge upon radius. As this charge will go on increasing, this potential will go on increasing. So potential increases from 0 to 16 volt, that is what they are given in the statement. But till then, how much time should we wait? That time we have to find out. This k as it is, this is total charge of This many electrons emitted in 1 second multiplied by total time. Come on. How many electrons are emitted in 1 second? This many, correct? That is n number of electrons are emitted in 1 second. In 1 second this many, then in t second how many electrons are emitted? N into t, correct? But that many electrons have how much charge? That number multiplied by magnitude of charge of one electron, correct? So n into E into T. Say everybody, n into E into T, correct? Fine. This capital as it is, this potential they have given in the statement. Come on, 16 volt, value of small k. This is proportionality constant coming in Coulomb's law. You must remember from third semester, 9 into 10 raised to 9 Newton meter square upon Coulomb square. What about small n? That is number of electrons emitted from the surface of sphere in 1 second, 2 into 10 raised to 7. Same number I am writing here. T we want to find out magnitude of charge of electron, how much? 1.6 into 10 raised to minus 19 Coulomb. What about radius of the sphere? They have given 10 raised to 2 meter. Because all the values are placed in SI units, naturally time will be obtained in second. Answer is 55,578 that many second. But by chance if they ask this time in hour, you are going from second to hour, so divide second value by 3600. When this second value is divided by 3600, final answer is 15.438 that many hour. Okay, come on my dears. Let us study today one article about alpha decay. What do you mean by decaying? Decaying means decreasing, diminishing, okay, deteriorating. Fine. In what sense this word is used here? Decay, D-E-C-A-Y. Decay means, look, you know, whenever any radioactive element is there, it would simply emit alpha or beta particle and will get transformed into new element. The original element is called parent element, newly formed element is called daughter element, correct? Fine. So what happens as time passes on? In a parent atom, number of undisintegrated atoms goes on decreasing. Decreasing means decaying. So you can say parent element decays. But as time passes on, there is a growth in the daughter element. So for a daughter element, there is a growth curve, and for parent element, there is a decay curve. Okay? As parent element decays, the daughter element grows. Okay? Fine. Here we are supposed to just discuss about decay processes. Radioactive nucleus can decay through 3 different types of processes. Which are they? Alpha decay, beta decay and gamma decay. Let us see all of them one by one. First of all, we would like to see about alpha decay. Fine. Let us consider the example given in textbook. Consider this radioactive nucleus 92 uranium 238. What does it do? It emits alpha particle, that is helium nucleus, that is 2He4, and after that it gets transformed into this daughter nucleus, which is 92 minus 2, that is 90, with atomic number 90. In the periodic table, the element is thorium, and 238 minus 4, that is 234. Correct? Fine. Now tell me, this parent nucleus gets transformed into this daughter nucleus. At that time, alpha particle is emitted. We find that emission of alpha particle is based upon probability. See, before alpha particle is emitted from particular nucleus, actually it is already have come into existence some time before. But it is not necessary that as soon as alpha particle comes into existence, immediately it will be emitted, not necessary. out of very large number of uranium nuclei in which alpha particles have been already formed, then also only some uranium nuclei are successful in emitting alpha particles. So remember, emission of alpha particle is based upon probability. Okay, there lies some definite probability for a given nucleus to disintegrate through alpha decay in a given time interval. Okay, fine. Here, this alpha particle is emitted with some energy. It means to say that in this process some energy is liberated. But how it is possible? See, we are not supplying any energy in the input, and then also energy is liberated. It means to say that in this process some mass must have been decreased, and that's why whatever is the decrease in mass, its equivalent energy is getting liberated. Okay, so let us find out decrease in mass in this process. Decrease in mass is there, so initial mass is bigger, final mass is smaller. Initial mass is mass of uranium nucleus, that's what I have written here, Mu, mass of uranium nucleus, minus final mass is smaller, but final mass is summation of these two masses, so mass of thorium plus mass of alpha particle, correct? This final mass I should subtract from initial mass, and that is how you are going to get decrease in mass. And if you want energy equivalent to that delta M value, that is mass difference or mass defect, then you should multiply by C square. This mass difference you must multiply by C square, then you will get energy equivalent to decrease in mass, correct? And that is the energy which will be liberated. Okay, fine. Now let us go for understanding another type of decay, which is called beta decay. If radioactive nucleus emits beta particle and then gets transformed into daughter element or daughter nucleus, then that process is called beta decay. But remember, there are particle and antiparticle. We have to study such two pairs in this article about particle and antiparticle. First of all, let us see about which are the 2 points of difference and similarities between particle and antiparticle. Which are the similarities between particle and antiparticle? Remember, they both have same amount of mass. Okay, that is first similarity. And second similarity, if both of them have charge, then magnitude of charge is same. Magnitude of charge is same. Okay, so these are the 2 points of similarities between particle and antiparticle. And which are the 2 points of differences between them? First point of difference is that their charges have opposite polarity. If charge of particle is positive, then charge of antiparticle is negative. And another point of difference, the directions of their spin are opposite. If the direction of spin of particle is say clockwise, then direction of spin of antiparticle would be anti-clockwise, like that. Okay, then out of such a pair of 2 particles, if you take one as a particle, then the rest should be treated as antiparticle. Let us see about one such pair, that is known as electron and positron. Electron and positron are the antiparticles of each other. If you take electron as a particle, then positron is its antiparticle. Okay, here in this article, electron will be shown now onwards by any of these 3 symbols. Which are these 3 symbols? Look here, -1 E0, or beta negative, or E minus. They all indicate electron. Okay. Similarly, there are 3 symbols for positron also. Come on, +1 E0, beta positive, or E plus. Okay. Mind well, whether it is electron or positron, both of them are called beta particles. electron is beta negative and positron is beta positive. Negative beta particle means electron, positive beta particle means positron. Sometimes we call positron as positive electron. The words positive plus electron, when you combine, the new word we have prepared, that is positron. Got it? Fine. So these are the various symbols for electron. These are the various symbols for positron. What are electron and positron? They are antiparticles of each other. Correct? Fine. Now, whenever any radioactive nucleus emits beta particle, at that time either proton is getting transformed into neutron or neutron is getting transformed into proton inside the nucleus. So let us see both the processes. If proton gets transformed into neutron, then positron is emitted, that is E plus. And if neutron is transformed into proton, then electron is emitted, that is E minus. Fine. Now here in both the processes, one more additional particle is also emitted. This particle has got three characteristics. First, its rest mass is nearly zero, not equal to zero, but nearly zero. It is a very, very light particle whose mass is negligibly small. Okay. Second characteristic, it does not have any charge. It is totally chargeless. And third characteristic, its spin angular momentum is having magnitude 1 upon 2 into h upon 2 pi. Spin angular momentum has magnitude 1 upon 2 into h upon 2 pi. That is 1 upon 2 into, h upon 2 pi is also known as h cross or h cut. So 1 by 2 h cross. Such a chargeless particle having spin angular momentum half h cross and whose rest mass is nearly zero is given a specific name, and that specific name is neutrino. What is it? Neutrino. And neutrino is shown by symbol this way, nu. Correct? Fine. And this is neutrino, and its antiparticle is known as antineutrino. What is it called? Antineutrino. And if neutrino is shown by this symbol nu, then antineutrino should be shown by this symbol nu bar. Nu bar. Okay, fine. Now tell me, this is the way you should put the symbol and how to pronounce nu, Nu. Correct? That is for neutrino. And how to pronounce this symbol? Nu bar. That is a symbol for antineutrino. Here we find that when proton is getting transformed into neutron, at that time neutrino is emitted. And if neutron is getting transformed into proton, then antineutrino is emitted. So nu bar. Just to remember, you remember that two bar signs are coming together. Okay? And charge wise, if you check, what is the charge of one proton? That is plus E. And here, come on, neutron does not have any charge. Neutrino also does not have any charge. So charge of proton and charge of positron, they are same. Here, neutron does not have any charge. So if initial charge is 0, then final charge also must be 0. Charge of proton and charge of electron, if you add, total charge is 0, and antineutrino does not have any charge. Okay? So there is a conservation of charge. And what about the example? Here 11 sodium 22 gives 10 neon 22 plus 1 E0 plus neutrino. You can check the atomic number and atomic mass number, you can check. 10 plus 1, that is 11. With atomic number 11, there is an element in the periodic table called sodium. 22 plus 0, that is 22. Correct? And what about here? Example is 15P32, that is P means phosphorus. Here 16S32, S means sulfur. Then electron is emitted, so minus 1 E0. At the time antineutrino is emitted, so nu bar. Okay? Check the atomic numbers and atomic mass numbers. 16 minus 1, that is 15. With atomic number 15, in the periodic table we have element called phosphorus. And 32 plus 0, that is 32. Got it? Fine. Here, this neutrino and antineutrino, they are such light particles, they almost do not make any interaction with any other materialistic particles. And because their masses are so small and because they do not make almost any interaction, their presence was checked experimentally after several years. It took several years time to just predict about existence of such particles. Okay, so nowadays we have come to know that such particles really exist, but their masses are negligibly small. Almost they do not produce any interactions. Okay, fine. Now we go for gamma decay. Gamma decay. See, if any radioactive nucleus emits gamma radiation and then after it is getting transformed into unexcited state, then such process of decay is called gamma decay. Fine. Normally what do we find? That parent nucleus first get transformed into daughter nucleus, and sometimes it so happens that even after coming into existence, the daughter nucleus is found to be unstable in the excited state, and then what does it do? It emits excess of energy in the form of gamma radiation and it comes to ground state. Okay, fine. Now what else we know about this nuclear energy levels? I am telling you. The way electrons in an atom have definite values of energy, and thereby total energy of atom is also quantized. Same way, there are definite values of energy for nucleons also in a nucleus. So if you find out total energy of nucleus, it is also having certain specific discrete values only. Then you can say they also have their own energy levels. Then what is the difference between atomic energy levels and nuclear energy levels? The difference is that, come on, in the atomic energy levels we have energy of the order of electron volt, whereas in nuclear energy levels we have energy of the order of million electron volt. That is the difference. Okay, so whenever any radioactive nucleus undergoes gamma decay, we are likely to have emission of photon of the order of having energy of the order of million electron volt. So at present, let us consider as if there is an emission of gamma ray photon with energy 1 million electron volt. If it is the case, then what is corresponding wavelength? Let us find out. Come on, energy of one photon, it is given by this formula, E equals to HF. Come on, H as it is. What about F? F equals to C upon lambda. F equals to C upon lambda. And this energy we assume to be 1 million electron volt. Let us find out now wavelength of corresponding radiation. Come on, lambda, make it subject of the equation, transfer it here, bring this E down. So lambda equals to HC upon E. H into C upon E. What are the values of H and C? Everybody knows. Planck's constant 6.625 into 10 minus 34 joule into second. C is the velocity of light in vacuum, it is 3 into 10 raised to 8 meter per second upon capital E, which is 1 million electron volt. But million electron volt is not the SI unit of energy. SI unit of energy is joule. First of all, convert million electron volt into electron volt, multiply by 10 raised to 6. And now 1 electron volt is 1.6 into 10 raised to 19 joule. Simplify, answer is 12.37 into 10 raised to minus 13 meter. Okay, but 10 raised to minus 13 you can split as 10 raised to minus 4 into 10 raised to minus 9. Simple. 10 raised to minus 9, if you associate with this number, then you get 0.001237, and 10 raised to minus 9 meter is nothing but 1 nanometer. So this lambda value is 0.001237 nanometer. Now this much value of wavelength is found to be in the region of gamma radiation in the electromagnetic spectrum. So radiation having such wavelength must be gamma radiation, correct? And that's why this process is called gamma decay. What is it called? Gamma decay. One very good example is taken in textbook. Look, here I have shown nuclear energy levels. Look, consider this nucleus 27 cobalt 60 and what does it do? It emits beta particle. When we say only beta particle, we mean to say electron, which is beta negative. And after emission of beta particle, the atomic number increases by 1 unit. So 27 plus 1, that is 28. With atomic number 28, element in the periodic table is nickel, and atomic mass number does not change. But now this nucleus is found to be in the excited state. When it is in excited state, what will it do? It will emit excess energy in the form of gamma ray, correct? And now it makes transition first of all into this lower energy level, and then after into this lowest energy level. When it transits from here to here, it emits a gamma ray photon with energy 1.17 million electron volt, and when it makes transition from this level to this level, it emits gamma ray photon with this much energy, 1.33 million electron volt. You can see, compared to this energy is more, this energy is less. That's why these two levels are close, and because this energy is more, these two levels are rather far. One thing more, because the energy lost in this transition is less, then frequency is less, then wavelength is more. And speak reverse, compared to this energy is more. More energy means more frequency means less wavelength. So here you can see wavelength is less, correct? Distance between two consecutive crests will give you wavelength. Here it is less and here it is more. Got it? And what is the difference between this and this nucleus? This nucleus was in excited state. It was having energy more than what is required to remain stable. And this nucleus has come into the ground state, that is in the minimum energy state, that is you can say unexcited state. Okay, fine. Now kindly read the statement of sum number 10, illustration number 10. Have you read it? Come on. What is the original element given to you? 92 uranium 238. Now tell me, what is its atomic number? 92. Z is 92. What is its atomic mass number? 238. Fine. What is the final product nucleus? 82 Pb 206. So what is its atomic number? Let it be Z dash, which is 82. And what is its atomic mass number? Let it be A dash, it is 206, correct? Now tell me, number of alpha particles emitted I just assume to be X, and number of beta particles emitted I just assume to be Y. As this nucleus gets transformed gradually into this nucleus, how many alpha particles are emitted, how many beta particles are emitted, that is what we have to find out. Now remember this formula. A dash equals to A minus 4x. Tell me, what is A? Atomic mass number of original element. What is A dash? Atomic mass number of new element. Then how this formula has come? Forgotten? See, whenever one alpha particle is emitted, atomic mass number decreases by 4 units. Look here. When one alpha particle is emitted, atomic mass number decreases by 4 units. That's why 238 minus 4 I had written here 234. When one alpha particle is emitted, if atomic mass number decreases by 4 units, then when X alpha particles are emitted, atomic mass number would decrease by 4x. So if you subtract 4x from atomic mass number of original element, you will get atomic mass number of new element. What is A dash value? 206, correct? What is A value? It is 238 minus 4x. From here you will find out 4x. Come on, transfer this, will become plus. Transfer this here, 238 minus 206 will give you 32. Then x will be 32 upon 4, which is 8. So what is number of alpha particles emitted? Come on, 8. Now let us find out number of beta particles this way. Remember this formula now. Z dash equals to Z minus 2x plus y. How this formula has come? Remember, if one alpha particle is emitted, atomic number decreases by 2 units. So, look here. When one alpha particle is emitted, atomic number is decreasing by 2 units. 92 minus 2, that was 90, correct? If one alpha particle is emitted, atomic number decreases by 2 units. Then if x alpha particles are emitted, then atomic number would decrease by 2x. Decreases, then I am putting minus sign. And whenever one beta particle is emitted, atomic number increases by 1 unit. Similarly, if y number of beta particles are emitted, atomic number would increase by y units. That's why I am putting plus y. Atomic number decreases, then minus, increases, then plus. Okay. So when you subtract 2x from z and when you add y, you will get common atomic number of new element. And what is z dash value? It is 82. Z dash is 82. Z is 92. Z is 92. Minus 2 into x. X is 8 plus y. Find out y from here. Y comes out to be 6. X equals to 8. Y equals to 6. X equals to 8. Y equals to 6. Number of alpha particles emitted is 8. Number of beta particles emitted is 6. Got it? Please remember this formula. How much is A dash? A dash equals to A minus 4x. You apply that formula first and later on formula of Z dash. Z dash equals to Z minus 2x plus y. Got it? Let us see what are called nuclear reactions. What are called nuclear reactions? In the year 1919, there was a scientist with name Mr. Rutherford. Mr. Rutherford. This fellow had proved experimentally that whenever any stable element is bombarded by some proper projectiles, proper particles with proper energy, that element is found to be getting transformed into new stable element, and at that time some particle is getting emitted. This very phenomenon is known as artificial nuclear transmutation. Artificial nuclear transmutation, and this very process is called nuclear reaction. I repeat, Mr. Rutherford had proved experimentally in the year 1919 that whenever any stable nucleus is bombarded by proper particles with proper energy, then it gets transformed into nucleus of another stable element, and at that time some particle is getting emitted. This very phenomenon is called artificial nuclear transmutation, and this very process is called nuclear reaction. Got it? Fine. Now let us consider one example. 7 nitrogen 14 plus alpha particle, that is helium nucleus 2He4, that gives 8O17, 8 oxygen 17, plus hydrogen nucleus, that is proton 1H1. Fine. The amount of energy exchange in the process is called Q value of given nuclear reaction, shown by symbol capital Q, which you must write only on right hand side. Okay? Fine. Now this very nucleus on which the particles are projected is known as target nucleus. What is it called? Target nucleus. This very particle which has been projected is called projectile. This is you are getting as a product, we call it product nucleus, and this you are making, you are having emission of this particle, this is called emitted particle. Come on, repeat it. What is this? Target nucleus. What is this? Projectile, that is projected particle. This is product nucleus, and this is emitted particle. Now tell me, because of reaction between these two, you are getting these two. If you change either of these two or both of them, then either of these two or both of them will change. In short, you will have a new nuclear reaction. New nuclear reaction. Fine. Now this nuclear reaction, if you want to show it symbolically, you may show it this way. A plus A gives B plus B plus capital Q. What is capital A? Target nucleus. What is small a? Projected particle or projectile. And what is capital B? Product nucleus. What is small b? Emitted particle. What is capital Q? Q value of given nuclear reaction. If you don't want to write this way, there is an easy and short way also. Capital A into bracket small a comma small b bracket over outside the bracket capital B. This is target nucleus. This is projected particle. This is emitted particle. This is product nucleus. Okay, fine. Now, what do you mean by Q value of nuclear reaction? It is going to show you the amount of energy exchange in a given nuclear reaction, correct? But how to find out its value? You need some formula. Formula is this. First of all, you find out difference between total mass initially and total mass finally. That is mass of reactants minus mass of products. And that difference of mass, if you want to find out equivalent energy, should be multiplied with C square. You know energy equivalent to mass delta M is how much? Delta M into C square. Delta M into C square. That delta M is right now, come on, summation of initial reactant mass, that is total mass of reactants, minus total mass of products. And that difference of mass should be multiplied with C square. Then the value of energy obtained is called Q value of reaction, shown by symbol capital Q. Now, if value of capital Q is obtained greater than 0, Q greater than 0, such a process is called exorgic process. Come on, exorgic process means that process in which energy will be emitted. That emitted energy we find in the form of increase in kinetic energy of reactants and also in the form of energy of some radiation, okay? And if a value of Q is less than 0, value of Q is less than 0, then such process is called endorgic process. What is it called? Endorgic process. And this process will not happen on its own. And then if you want it to make, if you want to make it happen, then you must supply energy in the input. If you do not supply energy in the input, such process, endorgic process, will never take place on its own. Got it? Fine. In such nuclear reactions, there has been found conservation of three physical quantities: charge, momentum and energy. Charge, momentum and energy always get conserved in every nuclear reaction. Okay? Now kindly read this statement of illustration number 11. Read it? Fine. They have given one reaction. 4 beryllium 9 is bombarded by alpha particles, that is 2He4, gives you carbon nucleus, that is 6C12, plus neutrons are emitted 0 and 1. Fine. Now just apply law of conservation of energy. Remember, in the law of conservation of energy, now we are going to include mass equivalent energy. Energy equivalent to mass, that also should be included here. Fine. Then according to this law, whatever is initial energy, same should be final energy. Now let us find out what is energy equivalent to mass of reactants. For that, you should find out total mass of reactants multiplied by C square plus kinetic energy of beryllium plus kinetic energy of alpha particle. That gives, come on, finally, you should find out energy equivalent to total mass of products. For that, total mass of products into C square plus kinetic energy of carbon plus kinetic energy of neutron. Come on. Mass of beryllium I am writing plus mass of alpha particle into C square. Kinetic energy of beryllium Kbe plus kinetic energy of alpha particle K alpha. Mass of carbon nucleus Mc plus mass of neutron Mn into C square. Kc means kinetic energy of carbon and Kn means kinetic energy of neutron. Fine. Now these two masses they have given in atomic mass unit. For beryllium they have given mass 9.012183 atomic mass unit. For alpha particle 4.002603 atomic mass unit. And if you have got this mass in atomic mass unit, then what is its equivalent energy? For that you must multiply it by 931.494 million electron volt, because it is given to in the statement that one atomic mass unit is equivalent to 931.494 million electron volts of energy. Come on, kinetic energy of beryllium. See, beryllium is here target nucleus. Target nucleus is at rest. Initially it was at rest, so naturally initial kinetic energy must be taken 0. And this projected alpha particles have energy, they are given in the statement 4.78 million electron volt. What about mass of carbon? They are given 12.000000 atomic mass unit. And mass of neutron, they are given 1.0086 atomic mass unit. And now once you get this mass in atomic mass unit, what is its equivalent energy? For that you must multiply by 931.494 million electron volt, because they have given in the statement that one atomic mass unit is equivalent to this much million electron volt of energy. And plus kinetic energy of carbon. Now they have asked maximum kinetic energy of neutron. See, when this term is maximum, it means to say this term is minimum. When you want maximum kinetic energy for neutron, this kinetic energy of carbon nucleus should be taken nearly 0. Nearly 0. So take this value as 0 and you will get now maximum value of kinetic energy of neutron, which we require. Simplify, find out maximum kinetic energy of neutron, that you are going to get 10.54 million electron volt. Got it?